So in question number 3 of this exam, I'm asked to find three different things. First of all, we're given that a 10.6 kilogram object oscillates at the end of a spring, and the spring has a constant K of 2.05 times 10 to the power 4 newtons per meter, and there is also the effect of a resistance that is represented by 3 newton seconds per meter. So first of all, I want to write the general solution to this system. So the general solution would be y double prime plus 2 beta y prime plus w naught squared y equals to 0. This is the general solution on everything. So now, the first question that I'm asked is to find the frequency of oscillation, the frequency of the damped oscillation. So first of all, I want to find the frequency at time 0, which is simply going to be equals to constant over the mass. So by plugging in the numbers, we have 2.05 times 10 to the power of 4 divided by the mass, which is 10.6. Of course, all the numbers have to work out for us. And therefore, we get, let me check, 2.05 times 10 to the power of 4 divided by 10.6. We get, and then the power of 1/2, we get 43.9768. Second power negative 1. But what does this mean? Well, it means that when we have a damped oscillation, so W1 is going to be equals to W0 squared minus beta squared. So now why this? Well, this is because it's a weak damping. If we had a strong damping, instead we would have had beta squared minus W naught squared on the square root for strong damping. I don't know. Damping. So what does this mean? It means that W1 is equals to, well, W naught, we just said it's this number right here. Duplicate it and let's bring it over here. And it has to be squared. Actually, so now what is our beta? Well, we know the beta is equals to B over 2M. And therefore, we have to take what we have before, so 3 divided by 2 times 10 to the power of, M was 10.6. 2 times 10.6, which is equals to, let me plug it in, divided by 2 times 10.6, which is 0.14151, about. This is rounded. So this squared, I take this, duplicate it over here, and then this minus, squared here, and then a square root. So if we take these two numbers, we square root them, and we subtract them, and then we put it to the power of 1/2, we will obtain 43.9766. And that's why I had to go in such detail with the numbers, because the oscillation is very, very weak, just 3 newton seconds per meter. So this is my final answer for part 1. This is going to be the frequency of oscillation for my damped oscillator. The second question is, by what percentage does the amplitude change? So we can say A1 is equals to a factor, so let's call it X, A naught. So what I want to find is by how much does the oscillation change? Well, let's look. Our general solution would be solved in something like this. Y to the power of t is equals to a, which is our oscillation, times e to the power of negative beta t cosine of our oscillation, our frequency times 1 times t minus a phase shift. So now the phase shift, we can assume it's equals to 0, and therefore yt is going to be equals to a times e power of negative bt cosine of w1t. So if I plug in 0, which I find the amplitude at point 0 is going to be equals to a e to the power of negative b times 0 cosine of w1 times 0, which is going to be equals to this cosine is going to be equals to 1. The e to the power of 0 is going to be equals to 1. So y times 0 is going to be equals to the amplitude. Okay, so it means that when we want to find it after a whole turn, so after a whole oscillation, we have to do something slightly different. We have to find out when cosine is equals to 1 again. Cosine, of course, of w1t, we said, is equals to 1. Well, this happens when t is equals to 0, when it's equals to 2 pi over w1, when it's equals to 4 pi w1, and so on and so forth. But we only care about the first one and the second one, because we care about how much it changes every oscillation. So if we take it, we already took when t is equal to 0, we have to take it when t is equal to 2 pi over w1. So let me take this formula again. Actually, no, let me write it as y with 2 pi over w1 is equals to a e to the power of negative b times 2 pi over w1 times cosine of this value here that I'm going to write again, but I'm pretty sure you already realize what it's going to be, 2 pi over w1. So w1 is related with each other, so we have cosine of 2 pi, which we know it's equals to 1, and therefore we have that y at 2 pi over w1 is equals to a times e, and then we said negative b, which is equals to the value that we found earlier, which was this one right here. We copy and paste instead of rerunning it. Paste times this value, so 2 pi over w1 that we said is equals to this 43.9766. Now, the more numbers you put, the more detailed it's going to be. So, if we plug this in the calculator, we're going to have that is equals to a times, so e to the power of negative 0.145151 times 2 times pi divided by 43.9766, which is equals to times, right, okay, 0.97998468670, right? So this value here will be about, let's say, just 0.988. As you can see, the change from initial A is going to be equals to 0.02, which, if we want to find the percentage, is going to be equals to times 100, so it's equals to 2%. So A1 is equals to A0 minus 0.02, they're going to write as 2% of A0. Or we can write this whole thing as A1 is equals to 98% of A0. But the change, of course, is going to be a 2% change. Now we're asked instead, when find the interval that elapsed while the energy of the system dropped to 5% of initial value. So let me write it down. point C is when energy at, let's call it say 0.1 is equal to 5%, 5% or at the initial value. So it means that it's going to be equal to 0.05 of E naught. So how do we do this? Well, we can look at the graph that we should have realized by now, and it's going to be equal to something like this. So we said that phase shift was equal to 0, therefore the value, our function starts at full amplitude. So this one is going to be equal to A, and then it decreases and decreases slowly as it goes. Now this one is a little exaggerated, but you get the point. Now, when we thought before, for example, the amplitude here is going to be equal to 98% the initial amplitude. But how do we find this? Well, this was simply going to be equal to, you realize by now, e at the power of negative pt. And if, for example, our system was shifted a little bit, for example, started here and was something like this. Let me do a little better. As you can see, the amplitude would still touch our graph. Therefore, the energy at this point in time will be equal to the amplitude at this point right here. So we can imagine that our system is a constant amplitude over time, because this is the energy that changes over time. So if we put it like that, we can say that we can just use potential energy. So U upon 1 is equal to 0.05 U at U naught. So that means that U at 0.1 is going to be equal to the 1/2 K A1 squared equals to 0.05 times 1/2 K A naught squared. Sorry, A squared is just for the A naught. Okay, so now we can cancel some stuff. So we now have 1/2 K and K, and we're going to end up with, as you can see, A1 is equals to 0.05 times, squared, equals to A naught squared. So as you can see, it's pretty easy to realize now that this A1 is going to be equals to A naught E, the power of negative BT, of course, squared, it will be, equals to 0.05 A naught squared. And we can erase the A naught because they're both squared on both sides. And we get that E, at the power of negative BT, is equal to 0.05. So let's put natural logarithm on both sides. We get negative BT is equal to ln of 0.05. Oh, sorry, here, the 2 is still squared, so it's going to be 2 beta t. So 2 over here. Now we divide both parts by negative 2b, so we get t is equal to negative ln of 0.05 over 2 beta. And we know that beta is equal to what we did before already. Let me go ahead and find the beta that we found before. So this value over here, copy. And let me write it over here. 2 times. So ln of 0.05 and time is equal to this. If we just plug in the calculator, we get the natural logarithm. ln of 0.05 divided by 2 times 0.14151 is equals to 10.58 seconds. Now you can add more numbers if you want, of course. It all depends also on the numbers that you got at the beginning, that you use at the beginning. Anyway, so this is the time that it takes for the energy of the system to reach 5% of the initial energy, 5.58 seconds, which is not a long time actually. Anyway, and that is how you solved this problem. Part A, B, and C.